Hello. Good afternoon, everyone. Welcome back to our quantum computing workshop after the lunch break. I hope you all had a refreshing break and are ready for the very exciting second half of the day. We have two very distinguished resource persons joining us now. First, remotely via virtual session, Dr. Ritajit Majumdar, and then in person, Mr. Gyan. I'm honored to introduce our first speaker of the afternoon, Dr. Ritajit Majumdar of IBM Quantum. Dr. Majumdar is a research scientist at IBM Angel Research Lab and works on quantum algorithm engineering aimed at making quantum computing real and accessible. He completed his PhD at Indian Statistical Institution, where the doctoral research focused on reducing resource uses and mitigating noise in discrete quantum computing circuits, a foundational problem for practical quantum computing. At IBM Quantum, Dr. Majumdar contributes to enabling both internal and external researchers to build utility-scale quantum applications using real quantum hardware. We are very fortunate to have friends today virtually, and I'm sure his insights will give us deep exposure into the realities of quantum computing and how research meets engineering. Please join me in welcoming Dr. Ritajit Majumdar. Okay. Yeah, thanks a lot for the invitation for having me here today. It was a very short notice, so I couldn't go to travel, but I have has been for the last few months regarding one started with the stakeholders there as well. Maybe largest portion of India, being one of the largest forests in the world. And I see that there are still more efforts in this workshop. I hope more efforts are going to come to really think that develop the workforce of India. One patterns. So I don't think there are people in Make patterns. Too much back on one's kind of more basic and prideful for a particular one. It's for example how that is. But today what I need to do is that I workshop of this workshop and give you a broad overview of what is quantum, why care and where quantum computing stands today. Okay, so let's dive into this. We are in this era of what we call as quantum computing, and it is quantum. So don't worry, you know, as quantum stands. How it all started, I'm sure many of you know. But you know, I mean, it's because Feynman first stated that you know all the simulations that we do of nature. So a very typical example I keep giving these days is say decision based. You must have heard of this term. The idea of decision based is that if body is different, if the human body is different. So there shouldn't be just a single medicine which we expect and want for everyone in terms of because my body is not the same as your body. Mechanism inside is not now, when we try to understand, so if you see, I'm sure many of you have seen, heard scenarios like this, where uh, you, the doctor and say, seems the doctor prescribes the same way, recovers until diagnosis. The medicine person A doesn't go as good for B. The second first that he has.
So all these things, what we have discussed, the fact that the body is like
వాయిస్ పిచ్ ఓకేనా? చెప్పు బాగుంది వాయిస్ పిచ్. ఏమన్నా ప్రశ్న గట్టిగా మాట్లాడు. కొంచెం ఇంకా యాక్టివ్‌గా మాట్లాడు. ఇంకా యాక్టివ్‌గానా? యాక్టివ్‌నే మాట్లాడు. ఏదో ఒకటి ఉంటది కదా! ఏదో ఒకటి చూడాలని కొంచెం యాక్టివ్‌నెస్సా? వస్తాడు కదా! అడ్రెస్
what we do
నెక్స్ట్ సెషన్ అయిపోయింది. అయిపోతే ఉండాలి కదా!
exactly generally this is how daily human body is born. And then we will develop skills. And when you do this, you lose out important information. Since you lose out important information, this is where these things come that one medicine work for me, didn't work for. These kind of all these kind of things come. And that's what Feynman said that see, when we take this kind of abstractions, the modeling that we do today using our computers, this is not correct. Even any even when happens in physics, chemistry, biology, everything, we have on the other hand, we are trying to do a simulation based on classical theory because quantum theory, simulating quantum theory is different. So this doesn't go hand in hand. This is what Feynman kind of meant. He wrote a paper following this document called Simulating Physics with Computers. For the first time, he got this down in some new branch of computer which we call quantum computer. Focus will exactly what on quantum computing or how before. But we kind of say that we in here when we have a branch of computing called quantum computing, we can use simulate ancient aspects. And that was in 1981. Today, simulating 2020, because right, we do have quantum computers. And we can think of all the problems that we want to solve. Uh, there are so many problems that we keep solving from our society, environment, everything, finance, so many important issues that we have today. There are already many problems which our classical computer can solve very quickly. For example, let's say that I ask you that you get 8 numbers and sort it. Yes, you can sort it very efficiently. There exists very efficient classical algorithms to do that. On the other hand, there are certain problems that we cannot really solve very efficiently using the cluster. So this will be all the NP problems. Um, what we do is that we one that we have so therefore it's continuity that it covers the subset of this new part. So we never claim that quantum computer will be able to solve every problem that we need to solve. That's not true. But it will definitely be able to solve a subset of those problems very efficiently. A general example is the integer calculus. So if I give you two numbers, still one, maybe you want to like doing the mathematics, but you can do it. On the other hand, if I give you a very large number by asking calculus, it is a more difficult to do that multiplication. It is more difficult for humans, and at the same time, this is even more difficult for our physical computer system. And based on this hardness, we have our custom ecosystems too. So all the security and everything, the most one of the most widely used mechanism is called this RSS ecosystem. And it relies on the fact that classical algorithms can be efficiently for very large numbers. So the point is not that this cannot characterize it. The point is not that I can with your security, but one example will be let's say you are doing so if you end up tracking your transaction of one data, it is no longer used. Which time is money in some sense. So if I do hack your transaction, like you get all the details of your transaction and do that in one point. Then your transaction and everything is done. I mean, it doesn't matter. But when you are doing transaction, like that doing different settings, then you are so that's what we need that integer factorization is kind of breaking this ecosystems. It's something which is very difficult for classical computers to do. Quantum computers are really application. But on top of that, there are certain things you see that this set goes outside. And this is the with errors. It goes outside. In kind of a quantum computer can kind of tracking problems, which are beyond what is well tracking sensible. For example, let's say simulating water elements as this. Simulating nature as it's something that you cannot do it scale. It's not like you have an efficient algorithm, less efficient algorithm, polynomial time, exponential time. It is not that. It is that you just cannot do it that way. I can do it efficient. Anyway, this same kind of goes inside. Let's take one. All these things I'm saying, and if you are always skeptical, and it's always good to be skeptical. Now, if you are skeptical, you can say that, okay, I mean, you are saying all this, but what if I a very powerful supercomputer? What if tomorrow someone comes up with an even more powerful supercomputer? Then do you that quantum computer? What if in next 10 years supercomputers become way more powerful than we are? Still, do we need a quantum computer? We can always ask this question. So let's, let's try to be skeptic and say that we have very powerful supercomputers, and maybe in next 10 years the supercomputers will be even more powerful. So, but we don't need a quantum. Let's take an example. This is the caffeine pop that we need. So let's assume that I want to understand the properties of this caffeine. And if you want to understand the properties of this caffeine molecule, then just to represent this molecule on a classical computer, you would need 10 to the power 14 bits. So just give it a second. Just to represent this molecule, the configuration of this molecule using a classical computer, you would need approximately 10 to the power of 12 bits. And that is around 1 to 10% of the total annual. So, and of course, this is not the most complicated molecule we have in our universe. You don't want to study more complicated molecules for, say, battery discovery, green energy, all of these things, with sustainability, all of those things. You really need to study some more, these are really more complicated molecules. So, what I mean here, you can understand that the point here is not how this question you have to take this point how could these supercomputers will become in 10 years? You cannot like 10 to the power something if you cannot end the movie 10% of what happens in the just change this you you can just the as one. Now this is the that I want that you take that action when I say take per point down to 160. So you can understand how much powerful it is. And the point is that there are problems like this problem I'm talking. There are problems whose solution is not like having more powerful supercomputers. These problems that you want to study the nature at this kind of scale, it is inherently quantum and you need a different round of cognitive quantum. The answer can never be that let's have a more wonderful story. Here is the 100 years of quantum mechanics, perhaps you know that, and yeah, like quantum mechanics, quantum computing is one of those student back for the bill, for the physics Nobel Prize was given for that. Even if you don't want to pay for it, but this year the Nobel Prize was given for kind of creating uh, the transmon thing, the superconducting quantum computers that IBM, Google, they have used this transform technique. The Nobel Prize in Physics was given for that. So it's kind of 100 years of quantum mechanics, and it is getting to be recognized at every point. And this is just the beginning. It is the 100 years of quantum mechanics, but this is for the first time we are getting Nobel Prize when directly linked to quantum computing. Previously, 2 years back, in CHS inequality, we can argue that it is more of quantum mechanics thing and not quantum computing. But the fact that this year's physics Nobel Prize is going to transform, of course, is superconducting and everything, but it is directly used to build quantum computers. So, yeah, this is just the beginning, and this is the time to grab the opportunity. So, okay, all these things and everything just discussed, but let's come back and answer a very small question that what is a quantum computer? What are the principles? Right? So, the working principle is very simple. If you think of a classical computer, what happens in it? Uh, we write algorithms and everything, and then it goes to a compiler, it breaks it down into assembly level language. Eventually, it gets broken down to bits. Right? We are so quantum computers are really younger compared to classical computers. So when you think of classical computers, unless you are very interested in working with hardware, you don't really worry about bits, logic, gates, or you worry about the algorithms or in that. But we are not at that stage where we can just think of quantum algorithms and forget everything about the circuit. We have to think in the circuit. So in classical computers, we start with build algorithms, as I said, we break it down using compilers, assembly table language, and then we come to bind bits. So the unit of computing there is bits. What happens to the bits? We apply some logic, select and gate or gate, not gate, NAND gate, or gates. We apply some logic gates which evolves the bits and finally measure. So what would mean the measure? I mean, you have to check whether the bits are zero or one. So we have to measure. And perhaps you have already taken some digital electronics classes where you use breadboards and then say you put some light source even if one one. And this kind of things so these are measurements. The same thing we will do in one physics. With the units, which is bits, evolution of bits, which are logic gates, we measure the bits. Instead of bits, in one second, we have quantum bits or qubits. What is the difference? The difference is very interesting. So, what are bits? The bits are either zero or one. In a quantum bit, a qubit, so if you draw a sphere like this, it is not necessarily a circle, it's a sphere. If you draw a sphere like this, every point on this sphere is a valid quantum bit, is a valid qubit. Okay? So it's not just like this is only zero or one, it is like every point in this sphere is a valid qubit. Which means if you think that qubit can be 0, qubit can be 1, qubit can be anything between 0 will not miss one bits. Once we get the qubits, we need to evolve them. Previously, we were evolving using some digital logic gates. Now we are evolving using some quantum gate. Here, these are quantum gates. And once the system evolves, we will measure. That's I mean, just like in classical system we have a exact equivalence in quantum systems. What is different, as I said, that the can be both 0 and 1 at the same time. So we know this is 0, we know this is 1. If my qubit is somewhere here, what will you call it? It is some a times 0 plus b times 1. Something, some values of a and b. So It is as if it contains both pieces of information, both zero and one at the same. Now you can ask this question that okay, you can have a qubit here which is closer to zero far away from one. You can have a qubit here which is not distant from zero one. You can have a qubit here which is closer to one far away from zero. Uh, what does that mean? How does it work? Okay. The point is that there is a slight difference in measurement from classical to quantum. In classical, the bits are either slow or not, and you measure whether it's slow or slow. In quantum, we are saying that the bits are in something called a superposition. This is called a superposition. It is both zero and one at the same time. But when you measure it, this collapses. What I mean by collapses, when you measure, you cannot see A0 plus B1. You see 0 with probability mod B squared, 1 with probability mod B squared. Fine. So when you measure this state, you either get 0 or you get 1. So now think, if my qubit is actually here, which is closer to 0, far away from 1, then when I measure, the probability of getting 0 is, if it is midway, then it is equiprobable that 0 than 1. If it is here, the probability of getting 1 is higher, 0 is lower. So it depends on the values of A and B, and the values of A and B tells me how far it is from this to say North Pole. This is how the qubits change. Almost limits. Let's think of case. We said that we can evolve the system. Let's first start with a very simple case where the qubit is well, remember qubit can be zero, qubit can be one, it can be combination of both, which we call as superposition. So let's assume that my qubit is zero. There is something called an H state, which is essentially a NOT gate. It takes 0 to 1, and takes 1 to 0. Now, when we set the state 0, and if I measure, then when you always get the outcome 0, there is nothing like 50% 0, 50% 1, nothing like that is there. I will only get the outcome 0. Now, when I apply the X state, it will flip. And now if I measure, I will always get the outcome 1. So at this point, I will always get the outcome 1 with probability 1. But this gate can also act on superpositions. So I can also take A0 plus B1, convert it to B0 plus B1. So now previously the probability of getting 0 was A squared, now my probability of getting 1 is A squared. This is how it changes. We can have other gates as well, like you start from 0 and then you apply something called a Hadamard gate. Even with break here, you just start to get how slow. So it's 50. So you can see that kind of measure this using the probability 0.5 to 1.5 to 21. Right? So this is how the systems evolve. These are cumulative operators. Mathematically speaking, any quantum gate is a cumulative operator, or vice versa. Any cumulative operator is a math. So this is what we are not only instead of you. You can have many gates that come up with your own cumulative operator. That you will have one. Now you can ask this question, and you should ask this question: that what makes computer quantum computer? And you will see many people will say that computers which follows the laws of quantum mechanics are quantum. This is completely wrong. Why? Because everything in this universe is created of electrons, protons, and neutrons. These elements they follow the law of quantum mechanics. So if you look into my laptop, if I look into my mobile phone, if you look into your mobile phone that you have in your pockets, all of them are made of electrons, protons, neutrons. That means they do follow the laws of quantum. So why are they not quantum computers? We are seeing that IBM has a quantum computer series. What is the difference? Okay. The difference is that when you have a quantum system, it has some certain phenomena. Like this superposition, we discussed about superposition. So it's as if that it is both in 0 and 1 at the same time. We have something called entanglement, where we won't go to mathematical details of this, where pair of few things which are entangled. Then, irrespective of the fact that we are thousands of kilometers away, if you do something on my qubit, your qubit, even though you don't do it, qubit, even though you are sitting thousands of kilometers away. So, as in, these are no individual qubits, but we cannot treat them as they are a single unit. This is why we use cryptography also in quantum. Then there is another property called Iiit. So you must have gone to seashore beaches. You have seen this. Next time when you go, see this more carefully. When a wave crashes, the water comes in inside the beach and is resides. It goes back to the seas. So when it is receding, for the next wave crashes, the next water comes in and these two collide. So one water is coming towards the beach, one water is receding from the beach, and these two collide with each other. When they collide, either they are oh, wave suddenly becomes a bit higher, or the wave goes down as fast. When it becomes a bit higher, this is called constructive impedance. When it goes down and it kind of the water is more of its tail, it is called destructive impedance. In quantum world, we have studied this in high school. We have what is called a wave particle one. So every particle thing has a wave, and this is how computing occurs in quantum systems. When we think of each wave as some potential candidate solutions, and when the waves collide, you want your correct solution to become high and the other solutions to die down. So these are the properties, and these are the properties that we don't really experience in our day-to-day life, in our macroscopic. So even though my laptop, my mobile phone, all that critical infra programs, you cannot really exploit this quantum data. But if you have a system which can exploit this feeling during computation, that's when I will create a quantum computer. Right? And that is what we mean that okay, IBM has a quantum computer and it is not the same as the computers that we are using at this. So that's what a quantum computer is. And as we discussed before, that it's a completely new branch of computing. And now, after discussing this, you must understand, so you must be understanding this that this is something different. No change, no supercomputer, no HPC, nothing will be able to do this because we are not exploring these things. So if exploiting these things give us some power, what cannot be utilized by supercomputers, however powerful, right? So what can we do with this quantum computer? So I think I hope that we now understand at least in the overall words into what are qubits, what are qubits, what happens when we measure the qubits, what makes a quantum computer quantum. All these questions I hope we understand more or less now. The question is that what can we do with the quantum computer? So we can do a lot and lot of things, but we can divide it in broad domains. One is ability check. This is something I have been talking about from the beginning. Understanding physics, understanding chemistry, understanding bioscience, all of that require nature, which are part of the nature and we want to know how systems evolve, how things evolve. These are something that quantum computers can do way better classical computers. There is something that quantum computers can do very well, is finding patterns and structures. So patterns and structures, where are they used? First, machine learning patterns. This is something quantum computers can do very well. Whenever you have so just talk about the short algorithm breaking ecosystems. That is also basically number theory. So these are some such chips that computer has to recognize. These are certain things that a computer can do. And finally, search and optimize. Optimization problem is able. Say, say you are trying to say you are trying to for think of this. You are organizing this workshop. You need to decide the budget. You need to decide when the workshop will happen. You need to find out when the students are free, when the speakers are free, how to organize, who can travel, cannot travel. All these things are very big optimization problems. Say you want to understand how finance works, how stock market goes up and down, these kind of things, search problems, those are again something that one can do very well. So this is the roadmap. This is the roadmap of the IBM quantum. Just give me this. Yeah, sorry. This is the roadmap that we have. The one first quantum computer in IBM came from 2016. Today we are starting at 2025. If you are trying to understand it started. We started with very small systems, computer systems, and 2026 up 2023, it kept evolving, and when it was in my opinion, it's so new that came to have a huge game where any or any general transaction or huge space for us and and 2020 one considered in US and we see that in the capital of France and women infants in the capital. This is how much it has evolved in 70 years. Going from 2023 to 2025, we have our most power we call that we have it comes with art, some kind of the family one and the R1 is a 133 qubits, R2 is 156 qubits, and we don't need to go into this too much. But just to give you an idea, the quantum computers are noisy, and you can see that from the previous bits that we had, it was the Eagle processor, and what we have today is the okay. You see how much the gate error has gone down, crosstalk is almost zero. The time of operation has gone down, say, 5 times here. And why am I showing you all things? Because this quantum computer, the 156 qubit quantum error quantum computer, in time will realize 10 on the GPU. So and I started by saying that this is the time that you should be knowing how the quantum computers, which are the problems that you want to tackle in the quantum computer, because you guys are going to have it like next to you, and if you don't know how to use it, then it's kind of a waste of effort. So once the quantum computer comes here, we all should be ready through our best standing and try to solve whatever problem you are interested in. Right. So that's why I'm showing you how much more powerful this Heron R2 is compared to this Eagle processor, which is there in many other, like the Cleveland Clinic one that I was talking about is an Eagle processor. So, but India is getting the Heron processor, yes, and we will do the it's, right. So I think that we need to be ready with our problems and everything, how to solve and everything, learning about quantum computing, learning physics, all of those things we should be ready with. But let's ask the question: what problem should we try to solve? I mean, why say this? See, there can be a lot of problems that you can solve using the quantum. So let's assume that you come up with something called quantum bubble solve, something like that. Is that a good problem? Yeah, sure. I mean, you have done some work and developed a quantum bubble solve. Is it an interesting problem? No. Because classically there are already very powerful bubble sort and we have very powerful sorting algorithms. So if you come up with a quantum sorting algorithm, perhaps that's not very interesting. So nobody stops you if you want to do that, but your research is not the problem. If you do this kind of steps. Now let's come to a setup. What are the interesting problems? What are the problems if I solve them the company finds it interesting? They value our effort, they value our research. What are those problems? Let's think of the prime factorization problem. Is it interesting the short algorithm? Yes, yes, of course, it is a very, very interesting problem, very, very interesting application of the problem. Yes. Now let's ask this question. I already started saying that quantum computers can break ice ecosystems very efficiently. How come our transactions are still secure? Because to break the to factorize numbers, like we use such huge bits today. To factorize those bits, you would end up requiring billions of bits, and I showed you we have 156 bits at this point. So millions of qubits is something which is not happening today, not happening anytime soon. You can understand. Going from 156 to a billion is going to take time. Right? So is it an interesting problem? Yes. Is it a binary problem? No. If you start by doing something like say short algorithm kind of thing, it is an interesting problem. It will be interesting in what you are doing, but that is not useful today. When will it be useful? We don't know. Let's be honest, we don't know. So we need to tackle some problems which are binary. What are these binary problems? Again, so we should understand this, but just to give you this idea, when you use quantum computer say here you start your research along this direction, looking at these binary problems. That gives you very powerful research papers that makes your paper stand out, that makes the community look into what you are doing. So what are these binary problems? If you think there are certain, as I kept saying, there are some very easy problems. Like how do you do addition? Well, our calculators, we don't even use calculators. So we have them inside our mind, right? You play video games, all of those things. You will have quantum computer. At the same time, there are some very hard problems like this short algorithm. We need to find at this point sweet spot to which are not really easy, not easy to the point where people can say that okay, whatever you are doing with quantum computer, you don't even need a quantum computer. Right? So it should not be that easy. At the same time, it should not be so hard that people will say that okay, oh, you have done this, but it will take you 20, 30 more years to actually go and do something. What are those sweet spot problems? The first and foremost area are this chemistry, biochemistry, condensed matter physics, material science, all of this. These are the areas which are already getting affected by quantum. We are already starting things which are way beyond what classical systems can do. Second, we have this optimization kind of problems. The combinatorial optimization that the graph problems that we all see when you study computer science, mathematics, we come across these graph problems. So irrespective of whether you are in computer science, mathematics, physics, chemistry, all of these problems are very near term and they can be very near term solutions to this. These are hard problems, so these are used to solve more towards longer. something that we don't expect to see much advantages quantum very soon are this machine learning and AI and problems. I know that quantum machine learning is a huge buzzword, but if you guys have worked on it, you also know that quantum machine learning is nowhere near to even performing what classical machine learning can. So maybe quantum machine learning can do a lot of things beyond what the traditional machine learning methods are able to do. Definitely not. So they are not in this at this moment. And finally, numerical simulations like this kind of short and this kind of they are like far apart. So if you are getting started, best is if you can focus your attention here. You can definitely, I know this is kind of a very strong interest for many people, but keep in mind that these may not be tiny problems. These can be interesting problems. These are perhaps not tiny problems. If you are looking for interesting and tiny problems, these are the areas where you should be focusing on. So where do we stand today? I started saying this era of quantum utility and what is it? So let's ask this question is today. Before we go into this, we need to just go back and think of that this heron process thing that I was showing that quantum computers are tools. Now see, if you will mind say that all the quantum gates are unitary matrices. So these are unitary matrices. Now you can do matrix calculation even on the classical one. So your quantum circuit essentially is a set of matrices multiplied with each other. Right? Some matrix vector multiplication. This is what your entire operation is. Now, if it is a small enough system, then you can just do that matrix vector multiplication on your classical machine. This is what we call as simulation. This is what we call as using a simulator. You just you use the method by which quantum systems evolve, but you don't use a quantum system. You simulate the technique of a quantum computer classically. So if you do that, there is no noise. Our classical systems are extremely robust. There is no noise in classical system. So all this fact that the gates have some error, there are some noise, measurements have some errors, and everything, all the errors which are in a quantum computers, they go away when you do a classical simulation. So you can ask this question that why should I go for a quantum computer when you are saying that these are erroneous, there are noise in the system? Why can't I just simulate that matrix vector multiplication on a classical code? You can. When you cannot, when this matrices becomes really big, and the size of these matrices scale exponentially in the number of cubes, right? So the way we will define a quantum utility is it is the point in time where quantum computers become better at each quantum computer. You can get very understand this definition. What do you mean? Quantum computers become better at being a quantum computer. What it means is that if you just try to do matrix vector multiplication on your classical machine, you try to simulate the effect of a quantum circuit, that you have a range up to which you can do, beyond which you cannot do, since the complexity of the problem grows exponentially. So we are at a point where you can run quantum circuits and you can run quantum circuits efficiently, not some noise coming in. You can reliably run quantum circuits beyond what these classical simulations can. Today we can do classical simulations on our laptop up to 32 qubits. Recently, I think 2 weeks back or something, there was some experiments where you could do classical simulation on an each PC up to 50 qubits. This paper, this cutting through the noise paper that was published in Nature, this showed an accurate estimation of expectation value on one of the 7 qubits. Now, see the point. I'm saying 32 qubits on your own laptop or desktop. Today, using HPCs, you can go up to 50, and here quantum computers producing is accurate distribution values. So, so at this range, you cannot go with the same, right? What's the problem that we solve? We don't want to go into very technical detail in this problem, but if you are from say physics or chemistry, this is called transfer sizing field. If you are from say economics or computer science, you can think of a sliding graph where each vertex is each arc is a vertex, and you have a succeeded each vertex. So these are the regions you have associated with each stage. And I'm trying to learn some property of that graph, which means in terms of mathematics, I want to, or in terms of physics, chemistry, I want to calculate the expectation graph. Now we start at okay. So this is basically called magnetization in terms of physics or something, but you can just think that I'm trying to learn some properties. Now we start with small systems, not immediately to one. We start with small systems where you can get the exact result. You can do the simulation on a classical computer and you can get an exact result. Now there are many approximate techniques, classical, not quantum mechanical. There are many classical approximation techniques which you can use. So at this range of 127 qubits, you cannot do matrix vector multiplication, but there are certain techniques called Pearson networks that you can use to approximately solve problems. Often these methods are used. So often these methods are used. So here we tried out both of them. We have the exact solution. We have this one-time solution given by this two dots. And we have classical approximation. This orange and this pink. And you can see that this point and this pink line are going away from the exact solution, whereas the quantum computer is actually sticking to the exact solution. So we slowly started making our systems bigger. So this was a very small system. We started bigger and it changes like this. Set result. The system is bigger, but you can still type. So you have this exact results. Again, the dot are your quantum results, and these are your approximate classical solutions. We made our system even bigger. So it is here also the same experiment. We see that this is the result, the blue line are the results from the quantum computer. This is the result from the approximate classical methods. Now, having shown this, just stick to what we just showed that as we start making our systems bigger and bigger, the classical approximate methods go more and more away from the existence. Point is totally different from this exact one is totally different from this exact. But the quantum result is still following the exact solution. Okay, now we go to a scenario. We go to this 127 qubit regime. Right? Number that exists. So you don't have that exception. This one because it's too big, you cannot do the calculation. Now the result that we take from a quantum computer are and this pink is the result that so the question to you is, we don't know which one is the exact, which one is the correct solution, but which one do you trust? I hope that he need to sort of probably informations. That understanding how closely it follows the exact solution, even if it still follows the exact solution as we go bigger and bigger systems, and we always get the classical approximate method just roughly. I think that at this point, you are more willing to trust the solution of this quantum computer and not the solution of the physical. This is what utility is. That you would rather go and trust the solution given to you by a quantum computer than an approximate classical one. So, if you are asked this question that at this age, would you use a quantum computer to run your circuit or would you use a classical computer to run your circuit? Your answer should be I should use a quantum. So this is what I mean that a quantum computer is better at being a quantum computer than just a classical computer is unable to simulate it properly. Now, what is shown here is that once we did that, there are many other papers came out after this paper was where people kind of proposed new approximate methods, and those approximate methods were not going. These methods are going very bad. This pink, this orange, but there are other techniques that people develop where they show that the results are agreeing with the quantum computers. So pretty much, not exactly, but pretty much, not so bad as this. Pretty much. So at this point, would you take that as a bad sign or a good sign? I would take that as a good sign. Why? For two reasons. First, it validates the solution of the quantum problem. Because here we don't have an exact solution. So it validates that the quantum is actually giving you correct results. Point one. Point two, I started by saying that quantum computers are noisy. So the struggle previously was that your classical, to simulate your system on a classical computer, they give you the exact. How can you make your noisy quantum computer produce the exact results? You see, the scenario change after this paper. Quantum computer is no longer struggling to keep up with the best classical methods. It is the best classical method, it is struggling to keep up with the best quantum method. So after this paper was published, people had to do more rigorous study on classical systems and try to match up with the result of the quantum computer. It is not the other way. It is not like a quantum computer is trying to match up with the best classical algorithm that we it is like the classical researchers are trying to cope up to the best quantum results that we get. So this is what changed with this huge paper. And this is where we are. At this scale, this is the scale where doing research makes sense. I'm never saying that you should, if you are beginners, I mean, you should be running circuits with 127 qubits, 2000 gates. I'm not saying that. It is of course useful to start with small systems and everything, but just as when we learn coding, we start by doing this hello world, we do all these for loops, different patterns, these are all useful. These are useful to understand integration of how these loops go and everything. Similarly, if you start with this small 5 qubit, 10 qubit systems, understand how things happen, understand the problem, understand how to write the codes. All of these things are important. But point is that after 2 or 3 years, you don't write code again after 2 or 3 years. Right? You don't write that. So if you are still using 5 qubit system, 10 qubit system after doing research for 2 3 years, then there is a problem. So that's what I mean that when you start today, in 2 years, you should be ready. You should go in that way that within 2 years, you are ready to start working at this scale. Because this is the scale where internationally people are working at. And if we are working at anything less than this, we are not doing research at the state of the art. We are just doing some non-profits. But this is not the only study that shows Meta scaling. Many other studies. I mean, this is huge now. This is not just only this. This is two big heads. So there are many studies going on. This came from IBM for the first time, but different other institutes are also doing that. IBM and other institutes. So it's not like only IBM is able to do this and you won't be able to do this. You should also be able to do this. Where we are going towards, see, at this point, why we call it utility? Well, of course, quantum is doing better. But you can argue that okay, people has been able to come up with Tensor network difference using really after the pattern basis. So you can still argue with me that no, no, I the goal to go from here is to go towards advantage. And advantage would mean that on real world skills, here you need examples of classical speedboats, concept, none of them can live up quantum discussion. So this is what we mean by advantage. This is where we should be struggling to go. And yeah, I still and this and show one small thing. There are these learning platforms. If you have not used this, please go and use this. Everything here is in. You can get started from the use of quantum information, see various algorithms, and then you have machine learning courses and everything. New courses have been added to this. In India, also, we are trying to build up a community, and this was from last year, 2024, what we call as quantum college. And we have been collaborating with many institutes. Today, we have two individual courses running. We have offered joint courses in quantum computing with different institutes. And of course, everything is like this one. Everything, these things are going. This was the quantum college last year. This year, we call it quantum E. And hopefully, we'll be able to things more and more every day. So start putting your effort, start investing in quantum computing, investing your time, your knowledge. You're going to see many of you in you know, this year. We hope something like this will happen next year. I'm going to have this. And we start with topics. So stop with that here, too. And
Thank you so much, sir, for such an insightful session. Dear participants, anybody from you would like to summarize what sir has explained till now? Anybody would like to summarize? No? If not, then we'll start our question and answer session. If you have any queries, questions, just feel free to ask. Sir will be very happy to receive and answer your questions. Anybody? Any questions? No? Anybody would like to ask anything to sir? No questions? Yeah.
Sir, how to contribute to the Qiskit community? Could you explain this?
so can you just repeat this question?
Sir, how can I contribute to the Qiskit community?
Oh, okay. That's a very good question and all. I hope you guys are already starting to learn Qiskit, use Qiskit. Qiskit is open source, so start putting the code of Qiskit. When you go into the Qiskit GitHub, you will see there are many issues which are there. People have found problems or enhancements that should happen, and they have put these things up as issues. In the issues, if you go and see, they have many tags. One of the tag is good first issue. So these good first issues are the tags, which means that these are the problems which require minimal knowledge of Qiskit and quantum computing to solve these issues. So I would say just go to the Qiskit GitHub, look into the issue there, look for the tags first issues, and start trying to solve one of those. At least let me start from there, and that will give you more confidence. When you look into these issues, that check all the first issues that there are, see which one you feel confident that okay, I can try to solve this. And when you can do that, just start doing that, submit a PR and everything. But this is how you get started. Start solving one or two of those first issues, and then slowly move up to a bit more complicated issues. Right, I hope that answers.
Thank you, sir. We have another question.
Sir, in problem hierarchy, we have three categories. Like one of the categories is interesting problems. So where you have given an example of prime factoring problem. So now, can we say that using this quantum technology, is it an easy problem now? Because prime factoring is a hard problem according to the classical computing. But can we now consider it as an easy problem?
No, okay. So if I understood your question,
Yeah.
yeah, so three hierarchies. This is interesting concept in factorization, but you can factorize very small numbers together because time factorization requires what is called as this fault tolerance. We don't have fault tolerance at this moment, but to break the security system, it uses I think some hundreds of thousands of bits at this point. Classical RSA ecosystems, you would end up requiring millions of keys. This is something that we cannot. We can, of course, factorize very small numbers today, but the reason I say it is not a timely problem is that if you show a quantum circuit or a quantum experiment, say that can factorize um, 21 or say 15 or something like that, these are not very interesting at this point. Because you can just do that on your calculator. You can just factorize that using your you are going to factorize say 121 or something like this. As long as you don't have a quantum hardware which can factorize at the scale where RSA cryptosystem is challenged, it doesn't become a timely problem. It is still an interesting problem, but if you want to really see your results on a quantum computer, then this is not a problem at this stage. That is why it's time problem. So, I mean, if you are focusing on that, you should be only able to show very small examples of factorization, not problems at the scale where it matters. That's why it's not final.
Actually, just I'm thinking in coming the security perspective, I mean, point of view. So where that prime factoring problem is a hard problem where it is used in the security of RSA algorithm. So in that way, just I was just trying to understand.
Yeah, I mean, that's my answer. My answer gives you like whatever you think for.
Yes, sir. Thank you.
Thanks.
Thank you so much, sir. It's a great pleasure having you here today with us. Any other questions? Anybody? Any more questions? Yes, please. Sir, we have another question.
Hello, sir. Good afternoon. So it's a bit off-topic question, but related to Qiskit. So I've been experimenting with Qiskit, and I found that many features like sessions and patches are not available on free time. So is there any alternative way to utilize the sessions or patches? Thank you.
No, not at this point. Not at this point. We can just hope that once the quantum comes there, we to have access at that point. It's not on once it is more of the Indian government. But once the access to the quantum computing is very good, so let's start steps. At this point, it's it's always pretty slow.
Still any more? Any more queries? No? Thank you, sir. Thank you so much for your time and for your insightful words. Great pleasure having you here. Thank you, sir.
And
Dear participants, before we proceed with our next session, let's wait for some time. Yella sir is here to join us.